We shall now discuss substitution rules for other types of functions. In this lesson, we shall cover substitution rules for cases that lead to logarithms, for exponential functions, for trigonometric functions, hyperbolic functions, and for cases that lead to inverse trigonometric functions. First, we have leading to logarithms. This is our formula. The indefinite integral of 1 over u du is equal to the ln of the absolute value of u plus c. Here, we let u be f of x, and we know that du is equal to f prime of x dx. For first example, we have find the indefinite integral of 3x squared over x cubed plus 4 dx. So using our substitution rule, we let u be x cubed plus 4, so the one in the denominator, and then du is equal to 3x squared dx. If we show the substitution, our given will be converted into, so 3x squared dx, as we can see, will become du, and then over x cubed plus 4 is u. This is the same as 1 over u du, integral of 1 over u du, and the answer is the ln of the absolute value of u plus c. Now, performing back substitution, we have ln of the absolute value of x cubed plus 4 plus c. For next example, we have find the integral of cosine theta over 10 plus sine theta d theta. So let us u be equal to 10 plus sine of theta, and then du is equal to the derivative of 10 is 0, while the derivative of sine theta is cosine of theta. Then we write d theta. Showing the substitution, we have cosine of theta d theta will be equal to du, while 10 plus sine theta, we have u. Now, since we are able to convert our given into d over u, we know that the solution will be ln of the absolute value of u plus c, and that if we perform back substitution, u will be replaced by 10 plus sine of theta, and then we write plus c. Example 3, we have indefinite integral of 4 over x times ln of x dx. Here we let u be equal to ln of x, and du is equal to 1 over x dx. Now, since we only need 1 over x dx for du, we are going to factor out 4. And so our given will now be, in substituted form, our given will be 1 over, so we replace ln of x by u, while dx over x will become du. And the answer will be 4 times the ln of the absolute value of u plus c. And then back substitution, we have 4 times ln of the absolute value of ln of x plus c. Next example, find the indefinite integral of e to the 4x over e to the 4x minus 10 dx. Performing our substitution, we let u be e raised to 4x minus 10, and then du is equal to, so the derivative of e to the 4x is e to the 4x times the derivative of the exponent, and that would be 4. And then the derivative of negative 10 is 0, so we just write dx. And observe that in our given, we need to introduce 4 and put a correction factor of 1 over 4 outside. Therefore, the given becomes 1 over 4 integral of, so 4 e to the 4x dx altogether will become du, and then over e to the 4x minus 10 will become u. So this is now equal to 1 over 4 ln of the absolute value of u plus c. Again, we do back substitution. We have 1 over 4 ln of the absolute value of e to the 4x minus 10 plus c. Problem number 5, we are given the indefinite integral of 12 over arc sine of 3x times the square root of 1 minus 9x squared dx. Now here, we let u be arc sine of 3x and we give its derivative. So du is equal to, so for arc sine of 3x, the derivative is 1 over the square root of 1 minus 3x quantity raised to 2 times the derivative of 3x, which is 3, and then we write dx. So simplifying, we get 3 over the square root of 1 minus 9x squared, then we write dx. So this is going to be our du. Now observe, in our given, we have arc sine of 3x will be replaced by u, but we have 12 over the square root of 1 minus 9x squared dx. In our substitution, we only need 3. So what we're going to do is that we factor 12 into 4 times 3. So we only factor out 4 and we retain 3 inside. So we have 3 over arc sine of 3x times the square root of 1 minus 9x squared dx. So again, the reason why we factored 12 into 4 times 3 is because we need 3 in our substitution. So this becomes 4. We have 3 times dx and then over the square root of 1 minus x squared altogether, that will become du. And then we have arc sine of 3x will become u. And so the answer here is 4 times the ln of the absolute value of u plus c. And we have finally 4 times the ln of the absolute value of u, which is arc sine of 3x and then plus c. For example 6, we need to find the indefinite integral of y minus 4 over y squared plus 64 dy. Following the formula for leading to logarithms, we are going to let the denominator be u, so that would be y squared plus 64, and then du is equal to 2y dy. Note that in the given, we only have, or we have y minus 4, whereas in the substitution, we need to have only y dy or 2y dy. So what we are going to do here is that we're going to separate the two terms in the numerator. This results to y over y squared plus 64 dy, and then we have minus 4 over y squared plus 64 dy. So for the first term, the substitution will be incorporated. We need to introduce 2 inside the integration symbol and then put a correction factor of 1/2 so that uh, the first term will become 1/2 integral of, so 2y dy will become du, and then y squared plus 64 will be replaced by u. And the answer to this one is 1/2 ln of the absolute value of u. So we'll just put the plus c later when we finish the answer to the second term. Now for the second term, we have 4 over y squared plus 64 dy. So we'll be factoring out 4. And if we recall the formula, the basic formula, we find that this is equal to 1 over 8 arctangent of y over 8, and then we put the plus c. So we have minus 4 times 1 over 8 is 1/2 arctangent of y over 8 plus c. We just have to perform the back substitution. So we have 1 over 2 ln of the absolute value of y squared plus 64, and then we have minus 1/2 arctangent of y over 8 plus c. So this is our final answer. For problem number 7, we will be finding the indefinite integral of x cubed over x squared plus 5 dx. So notice that the given is an improper fraction because the degree of the numerator is greater than the degree of the denominator. Whenever we're given improper fractions for the integrand, we need to divide first the numerator by the denominator. So let us show that solution. So we divide x cubed by x squared plus 5. So kindly recall how to perform long division. So here we divide x cubed by x squared. We get x, and then we multiply x or the quotient by the divisor. So we multiply x by x squared, or to x squared, we get x cubed. And then we also multiply x to 5, so we get positive 5x. And then we subtract this from our dividend. So we have x cubed minus x cubed is 0, and then we bring down negative 5x. Now, since negative 5x has a degree that is already smaller than that of our divisor, x squared plus 5, then this is already our remainder. So in short, we can now rewrite our given into, so instead of writing x cubed over x squared plus 5, we will write this as the quotient x plus the remainder 5x. However, since this is negative, so we're going to write this as minus 5x over x squared plus 5, and then we have dx. Now, to solve this, we are going to separate the terms. We have x dx minus, so let us factor 5, and then we'll have x over x squared plus 5 dx. So for the first term, the integral of x dx is x squared over 2. While for the second term, we are going to let u be the denominator x squared plus 5, and du is equal to 2x dx. Now, since we already have x dx in the given, we just need to put in a 2, and then 1/2 outside our correction factor, and perform the substitution. So this becomes 1/2 times 5 is 5 over 2. And then 2x dx will be replaced by du, while x squared plus 5 in the denominator will be replaced by u. And so we have x squared over 2 minus 5 over 2 du over u. The integral of du over u is the ln of the absolute value of u plus c. And then just perform the back substitution. We have x squared minus 2, x squared over 2 minus 5 over 2 ln of the absolute value of x squared plus 5, and then plus c. Our next rule is for exponential functions. So these are the formulas. We have integral of e to the u, du is equal to e to the u plus c. And for general exponential functions, we have the indefinite integral of a to the u du is equal to a to the u over ln of a plus c. So a here is any real number greater than 0, and it must not be equal to 1. Now, here u represents the exponent of the exponential function. For our first example, we want to find the indefinite integral of x times e to the x squared dx. So using the formula, we let u be the exponent of our given function or exponential function. So here it would be x squared. And then we get du is equal to 2x dx. Now, for the substitution to work, we need to make sure that everything in our given can be expressed in terms of u. So we have integral of e, we replace x squared by u, and then x together with dx. If we multiply this by 2 and correct that with 1/2 outside, then we now have our du. So we write here du, and using the formula, we have 1/2. The integral of e to the u is e to the u plus c, and then back substitution, we have 1/2 e raised to x squared plus c. Next example, find the indefinite integral of 8 cosine or 8 to the cosine 3x times sine 3x dx. So again, we let u be the exponent of the exponential function. So in this case, we have cosine of 3x, and then we get du is equal to negative 3 sine of 3x dx. So that we can substitute our given with the du, we have to multiply our given with negative 3 and correct that by putting negative 1 over 3 outside of the integration sign, which means we can convert now our given into negative 1 over 3. So 8, the exponent cosine 3x will be replaced by u, and then sine 3x dx times negative 3 will be replaced by du. Using the formula, we have negative 1 over 3. The integral of a to the u du is a to the u over ln of 8, and then you have plus c. Now we replace u with cosine of 3x. So we have a to the cosine of 3x and then over ln of 8 plus c. We now go to substitution rule for trigonometric functions. Here, we let u be the angle of the trigonometric function. And this is just an extension of the basic formulas introduced earlier in our class. So we have the following formulas. The integral of sine u du is equal to negative cosine of u plus c. And then the integral of cosine u du is equal to sine of u plus c. The integral of secant squared of u du is equal to tangent u plus c. Next, we have cosecant squared u du is equal to negative cotangent of u plus c. We have the integral of secant of u times tangent of u du is equal to secant of u plus c. And finally, we have the integral of cosecant u times cotangent of u du is equal to negative cosecant of u plus c. Let us now solve the following integrals. For number 1, we have integral of sine 5x dx. So here, the angle for our integrand is 5x. So we let u be 5x. And then du is equal to 5 times dx. Therefore, for the substitution rule to work, we must introduce 5 to our given and then correct that by putting 1 over 5 outside, so that our given becomes 1 over 5 integral of sine. So 5x for the angle will become u, and then 5 dx will be replaced by du. And then using the formula, the integral will be 1 over 5. The integral of sine u is negative cosine of u plus c. And then we perform back substitution. We replace u by 5x. For our next example, we have integral of x times cosine of 4x squared dx. So here the angle is 4x squared, and then du is equal to 8x dx. So 4x squared here will be replaced by u, and then x dx, if we multiply our given with 8 and put 1 over 8 outside, so we shall be able to perform the substitution. We have 1 over 8 cosine 4x squared will be replaced by u, and then x dx together with 8 will become du. And using our formula for trigonometric functions, the integral of cosine of u is sine of u plus c, And then we replace u with 4x squared. Our next example, find the indefinite integral of sine 4x cosine of cosine of 4x dx. So we let u be the angle, and that would be cosine of 4x. So here, this will be our u. And then du is negative 4 sine of 4x dx. We already have sine of 4x dx in our given. You just have to multiply this with negative 4 and then put negative 1 over 4 outside. We have our given. It becomes negative 1 over 4. So cosine of u, and then sine 4x dx and negative 4 will be replaced by du. If we use the formula, the integral of cosine of u du is positive sine of u, and then we have plus c, and then we have to write our given in terms of the original variable. So this will be sine of cosine of 4x, and then plus c. For the next example, we have integral of cosecant squared of square root of x over square root of x dx. So here, our angle is square root of x, which is the same as x raised to 1/2. Therefore, du is equal to 1/2 x raised to negative 1/2 dx. And this is the same as negative 1 or positive 1 over 2 square root of x dx. So our given becomes cosecant squared. We replace u here by u. Now dx over square root of x together with 1/2 will form our du, but we need to correct by putting the reciprocal of 1/2 outside, so that would be 2. And then we use the formula 2 times the integral of cosecant squared u is negative cotangent of u plus c. So this is the same as negative 2 cotangent of square root of x plus c. We now introduce other formulas for trigonometric functions. We have integral of tangent u du. This is equal to negative ln of the absolute value of cosine of u plus c. This is also the same as ln of the absolute value of secant u plus c. Next, integral of cotangent of u du. This is equal to ln of the absolute value of sine of u plus c. Next, we have integral of secant u du is equal to ln of the absolute value of secant u plus tangent of u plus c. And then integral of cosecant of u du is equal to ln of the absolute value of cosecant of u minus cotangent of u plus c. So notice that for these formulas, we are applying leading to logarithms. We also let u be the angle of the trigonometric function. Let us illustrate first the formula or the derivation for the formula of the integrals of tangent x and secant x. So we begin with tangent x. We are going to use the identity for tangent, and that is sine over cosine. And we let u be cosine of x, followed by du, and this is negative sine x dx. Now we multiply our given with negative 1, and then correct that by putting negative 1 outside, so that our given becomes negative integral of, so negative sine x dx will become du, and then cosine x will become u. So following our formula for leading to logarithms, this is negative ln of the absolute value of u plus c. Now we change u into cosine of x. Therefore, the formula for the integral of tangent x dx is negative ln of cosine, the absolute value of cosine of x plus c. Note as well that using the property for logarithms, this is equivalent to ln of the absolute value of cosine of x raised to negative 1 plus c, and this is the same as ln of 1 over cosine of x. So we put the absolute value. So finally, we know that 1 over cosine of x is the same as secant x. So the formula for the integral of tangent x dx, so we have either negative ln of the absolute value of cosine x plus c, or we can also use ln of the absolute value of secant x plus c. Now let's proceed with the integral of secant x dx. So here we are going to multiply our given with secant x plus tangent x. We do the same thing for the denominator. So essentially, we are multiplying our given with 1, and then we write dx. So we distribute secant x in the numerator to secant x plus tangent x. We have secant squared x plus secant x tangent x all over secant of x plus tangent of x dx. Now, we let u be the denominator, secant of x plus tangent of x, and that du is secant, the derivative of secant of x is secant x tangent x, while the derivative of tangent x is secant squared x, and then we put here dx. Now observe that du, which is secant x plus tangent x plus secant squared x dx, is just the numerator in our given. So therefore, we change that with du. And then the denominator secant x plus tangent x is just u. Again, this is just the ln of the absolute value of u plus c. And then we just perform back substitution. We replace u with secant x plus tangent x. And then plus c. So therefore, the integral of secant x dx is ln of the absolute value of secant x plus tangent x plus c. So the integrals for cotangent of x and cosecant of x may be derived in the same manner. We now solve the integral of x squared plus 2 times tangent of x cubed plus 6x minus 1 dx. So here we let u be the angle of tangent, and this is x cubed plus 6x minus 1. Then du is equal to, so the derivative of x cubed is 3x squared. And then for 6x, that would be 6. And then the derivative of negative 1 is 0. So we put here dx. And then we factor out 3, giving us x squared plus 2, and then dx. So if we perform the substitution, we notice that we need to multiply our given with 3, and then put a correction factor of 1 over 3 outside. So our given now becomes 1 over 3 integral of, so 3 times the quantity x squared plus 2, and then dx will now become our du. And then we have tangent, so the angle x cubed plus 6x minus 1 will be our u. And then the answer is 1/3 ln of the absolute value of secant of u plus c. And then we write 1/3 ln of secant of u, which is x cubed plus 6x minus 1 plus c. For next example, let us find the indefinite integral of cosecant of 1 over x squared dx. So we let u be 1 over x, and du is equal to negative 1 over x squared dx. So note that 1 over x is the same as x raised to negative 1. So we just apply the power rule to get negative 1 over x squared. Now, our given will be transformed into cosecant. So 1 over x will be replaced by u. Then dx over x squared is going to be du, but we need to multiply this first by negative 1, and then we put negative 1 outside. So the given becomes negative integral of cosecant of u du. And then we use the formula. So this is negative ln of cosecant of u minus cotangent of u plus c. And then we just replace u with 1 over x. So we have negative ln of cosecant of 1 over x minus cotangent of 1 over x. So that's absolute value and then plus c. We now go to the substitution rule for hyperbolic functions. However, we are going to consider only hyperbolic sine and hyperbolic cosine. So the formulas are, so the integral of sinh of u du is cosinh of u plus c, while the integral of cosinh of u du is sinh of u plus c. Here we have u as the argument of our hyperbolic function. For first example, we have integral of x times sinh of 8x squared dx. So here we let u be 8x squared, and then du is 16x dx. So notice that we need to multiply our given by 16 and then 1 over 16 outside. Again, performing substitution, we have 1 over 16 integral of, so sinh 8x squared will be replaced by u, and then x dx, and then 16 will now become du. So the formula for this is cosinh of u plus c, and then we just replace u with 8x squared. Now for our next example, we have integral of cosinh of the quantity x over x plus 1 all over x plus 1 raised to 2 dx. Now the argument is x over x plus 1. To get the derivative, so we have du. We will be applying quotient rule. So we square the denominator. We have x plus 1 raised to 2. For the numerator, we have derivative of x is 1. We copy x plus 1. And then minus, we copy x. And the derivative of x plus 1 is 1. So we put dx. And then simplify, we have x plus 1 minus x is 1 over the quantity x plus 1 raised to 2 dx. So this is our du. And our given becomes cosinh of, so x over x plus 1 will now become u. And then dx over the quantity x plus 1 raised to 2 is our du. And the answer will be, so the integral of cosinh of u du is sinh of u plus c, and then we just replace u with x over x plus 1 and then plus c. We now go to our last set of formulas for the substitution rules. We have cases that lead to inverse trigonometric functions. So we have the following formulas. So the integral of du over the square root of a squared minus u squared is equal to arc sine of u over a plus c. Next, we have the integral of du over a squared plus u squared is equal to 1 over a arctangent of u over a plus c. And then we have integral of du over u times the square root of u squared minus a squared. This is equal to 1 over a arcsecant of the absolute value of u over a plus c. So note that a is a constant greater than 0 and that u is a function in terms of x. For our first example, let us find the integral of x over the square root of 36 minus x raised to 4 dx. So here, a squared will be 36, and so a is 6. And then u squared is x raised to 4, and therefore u is x squared. Now du is equal to 2x dx. So observe that our given has x dx already, so all we have to do is multiply 2 here, and then we put 1/2 outside. So for the substitution, we have our given becomes 1/2 integral of 2x dx becomes du, while the denominator becomes a squared, square root of a squared minus u squared. And from our formula, this will be arc sine of u over a and then plus c. We just replace u by x squared and then a, we replace this by 6. So the final answer will be 1/2 arc sine of x squared over 6 plus c. For our next example, we have the integral of sine x dx over 25 plus cosine squared x. We let u be, or u squared is cosine squared x. Therefore, u is cosine of x. And then a squared is 25. So therefore, a is 5. Now we also get du, and this is negative sine x dx. So we have to multiply our given by -1, and then we also put -1 outside. So for the substitution, we have negative of, so negative sine x dx will now become du. And then for the denominator, 25 will be a squared, while cosine squared x will be u squared. And our formula for this is, so we have -1, and then we put in 1 over a, arctangent or tangent inverse of u over a plus c, and then we just replace a by 5, and then arctangent, we replace u by cosine of x, and then a again will be replaced by 5, and then we have plus c. So our final answer for the integral of sine x dx over over 25 plus cosine squared x is -1 over 5 arctangent of cosine x over 5 plus c. Our next example is uh, a case that leads to inverse secant or arcsecant. So we are given integral of 1 over x times the square root of 25x squared minus 81 dx. So recall that the formula for arcsecant, or the one that leads to arcsecant, has to take the form du over u times the square root of u squared minus a squared. So for our given, we let u squared be 25 minus 25x squared, which means u is 5x and that du is 5 dx. Next, the value of a squared is 81, therefore a is 9. So if we perform the substitution, we take note that the denominator has to have a u. So in this case, we only have x, but u is 5x. So we need to put a 5 and put on the numerator as a 5 as well. So that essentially we're multiplying the given by 1. Now, let us check whether the substitution will work. So for the numerator, we already have 5 times 1 dx, so that would be our du. For the denominator, we now have u, and then we have square root of u squared minus a squared. Therefore, it follows the form that leads to inverse secant function or arcsecant. So the answer would be 1 over a times arcsecant of the absolute value of u over a plus c. So we now perform back substitution. We replace a by 9. So we write arcsecant of the absolute value of u, where u is 5x all over 9 plus c. Our next example will be, we will be using both substitution rule for powers and leading to inverse trigonometric function. So our given is the integral of 3x minus 4 over the square root of 1 minus 4x squared dx. So for this problem, we are going to separate into two terms. So the first term will be 3x over the square root of 1 minus 4x squared dx, plus the other term will be negative 4 over the square root of 1 minus 4x squared dx. So we are going to solve each of these two terms separately. So for the first term, we have 3x over the square root of 1 minus 4x squared dx. We are going to apply chain rule for powers or substitution rule for powers, where we let u be the base 1 minus 4x squared and du is negative 8x dx. Now observe that for the substitution to work, our numerator should have negative 8x dx. But in our given, we have 3x dx. Therefore, we're going to factor out 3. So we're going to factor out 3, multiply our numerator with negative 8, and put the correction factor of negative 1/8 outside of the integration sign. So the coefficient will become negative 3 times 1 over 8 or negative 3 over 8. So if we show the substitution, what will happen here is that negative 3 over 8 times negative 8x dx will become du. And then for the denominator, we will have square root of u, which is equivalent to integral of u raised to negative 1/2 du. So continuing, the answer will be negative 3 over 8. Using power rule, u raised to negative 1/2 plus 1 is u raised to 1/2 over 1/2. So we'll just put the constant of integration later. So this will become negative 3 over 8 times the reciprocal of 1/2. So that is 2. And simplifying, we'll get negative 3 over 4. And we replace u by 1 minus 4x squared. So we have 1 minus 4x squared raised to 1/2, or negative 3 over 4 square root of 1 minus 4x squared. So this is the answer to for the first term. Now for the second term, we have integral of negative 4 over the square root of 1 minus 4x squared dx. We are going to use leading to inverse trigonometric function where u squared is equal to 4x squared. Then u is the square root of 4x squared, so this would be 2x, and that du is 2 dx. Now we also have a squared, and that would be 1, and that the value of a is 1. So if we show the substitution for the second term, we only need 2 dx for the numerator. And since we already have negative 4, we'll just factor 2 so that we will have negative 2 outside. And then we will retain 2 dx for the numerator. And then you have square root of 1 minus 4x squared. Continuing, we have negative 2 integral of 2 dx, so that would be du over the square root of a squared minus u squared. So if we continue, we have negative 2 arc sine of u over a. So u is 2x over a, which is 1. And so this is negative 2 arc sine of 2x. So we will now combine our answers to the first and the second term and then add a constant of integration. So the answer will be negative 3 over 4 square root of 1 minus 4x squared minus 2 arc sine of 2x and then our constant of integration c. Next, let us find the integral of x cubed plus 5x plus 10 all over x squared plus 4 dx. So we encounter here again a fraction where the numerator has a degree greater than the degree of the denominator. So this is an improper fraction. We need to divide first. So let us illustrate or let us show the division. So we have x cubed plus 5x plus 10 divided by x squared plus 4. So first we divide x cubed by x squared. We have x, and then we multiply x to x squared, so we get x cubed, and then we multiply it to 4, so we get 4x. And then subtract this, we get x cubed minus x cubed is 0, and then 5x minus 4x is x, and then we bring down 10. Now, the degree of the result is 1, which is less than the degree of the divisor. So this means the division is already complete. We are now going to write our given in the form quotient plus the remainder. So our given will now take the form integral of x, that is our quotient, and then our remainder is x plus 10 over x squared plus 4, then dx. So further, we uh, we will be separating this into terms and solve them separately. So we have integral of x dx. We'll do the same thing for x plus 10. So this will be x over x squared plus 4 dx. And then we have integral of 10 over x squared plus 4 dx. So the first term will simply use power rule. So the integral of x x dx is x squared over 2. And then for the integral of x over x squared plus 4 dx, so we are going to let u be the denominator x squared plus 4. So this is du, or du is 2x dx. So we need to put a correction factor. So first we need to put 2 in the numerator and then correct that by putting 1/2 outside. Therefore, the result will become 1/2 du over u, the answer of which is ln of the absolute value of u. So we put 1/2 ln of the absolute value of u, and u is x squared plus 4. So finally, we have the last term. This will be leading to inverse trigonometric function, specifically arctangent. So we copy the numerator 10, and then the answer is 1/2 or 1 over a. So here a squared is 4, so meaning a is 2, and u squared is x, therefore u is x, and du is dx. So our answer now is 1/2 arctangent of u over a, or x over 2, plus c. So let us just simplify. We have 10 times 1/2, so that gives us 5. So we're just going to erase this. So we have 5, and then arctan of x over 2. So the final answer is x squared over 2 plus 1/2 ln of the absolute value of x squared plus 4 plus 5 arctangent of x over 2 plus c. For next two examples, we are going to apply completing the squares. So for the first, we have integral of dy over y squared plus 16y plus 113. So note that if we let u be y squared plus 16y plus 113, then du is equal to 2y plus 16 dy. And we do not have that in our numerator. Hence, we are going to apply a different technique to solve this problem, and that would be completing the squares. So let us proceed. We copy the numerator dy, and then for the denominator, we are going to isolate the variables. So we have y squared plus 16y. We are going to isolate this from the constant 113. So our goal is to come up with a perfect square trinomial. Uh, and to do this, we will be adding an appropriate constant to y squared plus 16y. So that value will be obtained by dividing the coefficient of the linear term. So the linear term is 16y, the coefficient is 16. We divide this by 2 and we square it. So 16 over 2 is 8. And then square 8, or we square 8, that would be 64. So we now produce a perfect square trinomial. So y squared plus 16y plus 64 is a perfect square trinomial. The number that we added to this expression, we shall subtract this to the same number to the constant. So we added 64 to the variables or the first two terms, and then we subtract this to our constant 113. So we continue. We have dy for the numerator. We shall write our perfect square trinomial into y plus 8 squared. So y squared plus 16y plus 64 is equal to is equivalent to y plus 8 quantity raised to 2, and then plus, so 113 minus 64 is 49. So now we let u squared be y plus 8 quantity raised to 2. So therefore u is y plus 8 and du is equal to dy. Also, a squared is 49 and a is 7. So if we perform the substitution, our given will become du, the integral of du over u squared plus a squared, and the formula for this one is arctangent. So we have 1 over a arctangent of u over a plus c. So a is 7. So arctangent of u, or the value for u is y plus 8 over 7 plus c. So our last example is find the integral of 3x plus 1 over the square root of 15 minus 2x minus x squared dx. So this is a problem that requires the use of substitution rule for powers, as well as completing the squares and leading to inverse trigonometric function. So first we separate the numerator. So we have 3x over the integral of 3x over the square root of 15 minus 2x minus x squared dx. And then the second term will be uh, integral of 1 over the square root of 15 minus 2x minus x squared dx. So we shall solve these two terms separately. We begin with the first term. So we factor out 3, and then we have integral of x over the square root of 15 minus 2x minus x squared dx. So here we're going to let u be the base. So this is 15 minus 2x minus x squared, and the derivative is negative 2, or du is negative 2 minus 2x and then dx. So we shall factor negative 2. We'll have 1 plus x, or x plus 1 dx, and this is equal to du. Now for the substitution, observe that what we need is x plus 1 dx in our given, but we only have x in the numerator, so that we would be able to use the substituted form. We're going to add 1 to x. Now, since we added 1 to x, we need to ensure that we retain the actual given, which is 3x plus 1. So we need to subtract the value we added to the first term to the second term. So we added 1 to x, but since we factored out 3, essentially we multiplied or we added 3 to the first term. So we're going to subtract 3 to the second term. So here we're going to subtract 3 so that our given remains the same. Next, uh, for du, we need to have negative 2 as a coefficient. So we're going to multiply x plus 1 with negative 2. And then we are going to correct this by putting negative 1 half outside of the integration sign. So that would be our correction factor. So the coefficient outside becomes negative or 3 times negative 1 half or negative 3 over 2. So if we show the substitution, our given becomes negative 3 over 2 integral of, so negative 2 times x plus 1 dx will now be replaced by du over the square root of u, and this is the same as u raised to negative 1 half du. So we have negative 3 over 2. We evaluate the integral of u raised to negative 1 half du. So this is u raised to 1 half over 1 half. Again, we'll just include the concept of integration later. So continuing, we have negative 3 over 2 times the reciprocal of 1 half. We will be left with negative 3 and then u raised to 1 half. So back substitution, we replace u and then convert it into the radical form. So u is 15 minus 2x minus x squared. So for the first term, the answer is negative 3 square root of 15 minus 2x minus x squared. Now we move to the second term. We now have integral of 1 minus 3 over the square root of 15 minus 2x minus x squared dx. So this becomes negative 2 over square root of 15 minus 2x minus x squared. Now here we're going to perform completing the square. Again, we are going to isolate the variables from the constant. So let us also factor negative 2. So we isolate 15 and then we factor negative 1 so that our variables become uh, x squared plus 2x. So we need to identify a constant that we shall be adding to x squared plus 2x so it becomes a perfect square trinomial. So that value would be, so we check the linear term. The linear term is 2x. We divide the coefficient by 2. So that would be 1. So 2 over 2 is 1. And then we square it. The value is 1. So we add 1 to x squared plus 2x. And this now is a perfect square trinomial. Now this same value that we added, we should subtract it to the constant 15. However, since 1 is, we have negative 1 distributed to 1, so instead of subtracting 1, we're going to add 1 to 15 because we actually subtracted or we actually added negative 1 to x squared plus 2x because of the negative sign outside. So this becomes negative 2. So we also have dx. So this is 1 over. So 15 plus 1 is now 16 minus, we write our perfect square trinomial as x plus 1 squared and then dx. And we are now going to use leading to inverse, specifically arc sine. So the answer will be negative 2 arc sine of u over a. So here, u squared will be x plus 1 squared So u is x plus 1, and then du is dx, and a squared is 16, therefore a is 4. So we have the answer is negative 2 arc sine of x plus 1 over 4. And so this is the answer for the second term. Now we combine the answer to the first and the second term. So let's write our final answer. We have negative 3 square root of 15 minus 2x minus x squared, plus negative 2 arc sine of x plus 1 over 4, or simply minus 2 arc sine of x plus 1 over 4, and then we put in our constant of integration. So this is now our final answer.